Okay, Jai Hind all. So this is the today's topic is single fed control rectifier fed DC separately excited motor from the subject of electric drive, that is final year subject. That code is KEE075. So today I am going to discuss about this subject. It is from unit 3 of electric drive subject. So as you know, like drive system, because in the previous lecture we have discussed the drive system and the importance of drive system, because with the help of drive system you can control the flow of power and you can provide the power according to the load requirement, right? So here I am going to take a DC drive, and with the help of single phase rectifier system we are feeding the power. So here I have considered fully controlled rectifier. So in fully controlled rectifier, that means all four devices are this is the rectifier which convert the AC supply to the DC, and this DC is feeding back to the feeding to the motor, right? So this fully controlled, that means all four switching devices are thyristor based. So this circuit will operate in two mode, like discontinuous conduction mode and the continuous conduction. So we will see the analysis, we will do the analysis and we will see the performance of this drive system with by using this two mode of operation, right? So if we see that, like here I am going to draw again. So I just take the first I am just taking the continuous operation. This is the model of DC motor, how DC motor drive will model, like it has the armature resistance, the inductance and the back EMF, right? This is T1, this is T2, this is T3 and this is T4. So I am just taking the first continuous conduction mode. So in continuous conduction mode, first we will see how this system will operate. Like when you apply the AC inputs, the single phase, suppose Vs is applied here. So as then the AC voltage is applied here, so during positive half cycle T1 and T2 will operate, and during negative half cycle T3 and T4 will operate. So suppose the firing angle is, the thyristor firing angle is alpha, and now we will try to draw the waveform and find out the output voltage which is feeding output voltage, or you can represent by V0, which is feeding to the motor, right? So I am just drawing the waveform and try to develop the output voltage. So please like understand with the help of this waveforms. So suppose this is the input voltage Vs, the frequency is 50 Hertz. So I am just drawing here like this only, and we assume that the continuous conduction mode. The second condition also we will going to consider like discontinuous conduction mode, but first we have considered here the continuous conduction mode. Continuous conduction mode means the inductor value is very large and the current is continuous throughout the operation of the motor or the DC drive system, right? So here I am drawing the armature current and the output voltage. So armature current is continuous, like it is not phased with the current with the voltage, because it has, the circuit has the inductance also, right? Now we try to draw the VA. So V0, that is output voltage. So during, suppose the firing angle is alpha, so at alpha, when this positive half cycle, so this T1 is, T1 and T2 will be at, when this is during positive half cycle, this is positive terminal, this is negative. So this T1 and T2, because here is a positive, here is this comes as negative. So this, you can see that T1 and T2 will be in forward blocking state. Now when we fire this T1 and T2 at alpha, it will now come into the forward conduction mode, right? So when we come to the forward conduction mode, the voltage across the DC motor will be same as the Vs, and you can draw like till alpha to till pi, you are getting this, the same voltage Vs, right? Like that, right? So this is V0 during this period, pi, D0 to pi. Now, because it's a continuous conduction, so the current is continuously flowing through this IA, through the circuit. So when the negative, during negative half cycle, this terminal become negative and this has become positive. Now the T3 and T4 will be at forward, the forward blocking state, and the T1 and T2, still T1 and T2 is a forward because negative voltage is applied at T1 and T2, but still the current is flowing, so that still the current is flowing, so the T1 and T2 will not turn off, right? So by pi to alpha, pi plus like again alpha, here is the T1 and T2 will be fired, right? Now during this period, T3 and T4 will be this at this period, not this, at this instant of time, T3 and T4 will be fired. Right? Now we'll see like, so during, because still the current is, you are getting the current still in the circuit, so T1 and T2 is not going to turn off at this point. So till alpha, pi plus alpha, you are getting the voltage, right? Then again the T3 and T4 will be fired, like that you are getting this. So this is the initial point, right? So at continuous mode of operation, V0 you are getting this way, right? So that means alpha to pi plus alpha, if you find out the average value, you can easily find during alpha to pi plus alpha you are getting the voltage same as the VM voltage, right? So this is your V0, right? This is VM, this is VM, right? So average value of V0 can be find out. Vm cos sin omega t, integration is cos minus cos omega t, and that can be written as Vm by pi cos alpha. So you are getting here 2 Vm by pi cos alpha. So this is the voltage you are getting at the input to the DC motor, right? So this is the continuous mode of operation. Now if your circuit is operating in the discontinuous mode, that means the current is during the when the motor drive is operating, at some of the instant the current will be 0, right? So here I am going to now consider and if it is consider the discontinuous mode, but before discontinuous mode also you can find out the speed of the motor, right? Like according to the DC motor equation, E is equal to K phi omega m. So omega m can be written as E upon K phi, and E is equal to V minus IA RA V0 minus IA RA upon E. Sorry, it's K phi, right? So this can be written as V0 can be replaced by 2 Vm by pi cos alpha upon 1 upon K phi minus IA RA upon K phi. Now as it is a DC separately excited motor, phi is constant. So T is equal to K phi IA. So it can be T is proportional to or can be considered as TIA. So I can be replaced by this T upon K, so that speed torque characteristic can be drawn with the help of this formula, because if you want the characteristic between the speed and torque, you must have the relation between the speed and torque, right? So omega m is equal to just 2 Vm cos alpha upon K pi, this is K pi minus T upon K, this is Ka and Ra. So this is the relation you are getting between the speed and torque. With the help of this, we try to get the speed torque characteristics. We will see also in this. So this is for when the motor is fully controlled. So fully controlled, that means all the 4 devices you are using we'll see the half control also, but first in fully controlled, that means all the 4 thyristor, all the 4 devices are based on the thyristor. We can control on all the 4 both of the waveforms. We can control with the help of firing angle, right? So this is a continuous mode of operation. Now we'll see the discontinuous mode of operation, then we'll able to draw the speed torque characteristic. So this is so discontinuous mode of operation, that means during the motor operation somewhere the current will be 0, some duration or some instant of time the current will be 0, the armature current will be 0 now. This is T1, this is T2, this is T3 and this is T4. This is RA, L, A and this is A, right? This is back EMF of the motor. This is Vs, that is input voltage to the thighs to the converter, sin omega t, right? Now, so with the help of waveform, we can now understand the DC drive system separately excited. So this is suppose the input voltage Vs, the instantaneous value you can draw like this only. It has a maximum value is Vm. This is pi, this is 2 pi, and the frequency of this waveform is 50 Hz, right? Now just draw the current and the output voltage, right? This is the output voltage. I'll just wait. So this is V0 and this is suppose IA, the armature current, and it is discontinuous. So suppose the alpha is the firing angle of the thyristor and beta is the extension angle at which the current is 0, right? And suppose we assume that the beta is greater than pi, right? We assume that, right? So now, suppose at angle alpha, the motor will start from 0. And it is 0 at somewhere at this angle. This is beta, right? So we assume that the beta is greater than pi, that means the current is 0 after pi, right? Now from here at instant of alpha, the T1 and T2 become forward biased, forward conduction mode. So they are the current will flow through a T1 and T2 and you are getting the voltage across the motor is totally a Vs, equal to Vs, right? So till here you are getting the voltage like this, right? But and after that, because the current is still there at beta, till beta, so even though T3 and T4 is become forward blocking state, but we are not fire this T3 and T4, right? So it is in forward blocking state. So during pi to beta, the current is still there, even though T1 and T2 is experience a negative voltage, but the current still there. So T1 and T2 is not turned off till beta. So during pi to beta, you are getting the same voltage as Vs, right? So till beta, you are getting the same voltage, and after that, between beta to this is alpha, like again you are pi plus alpha, you can say. Again at pi plus alpha you are fire this T3 and T4, because at this state before this pi plus alpha at this state, because between the pi to pi plus alpha, the T3 and T4 is forward blocking state, right? So when the T3 and T4 is forward biased at pi plus alpha, because at beta the T1 and T2 will be turn off now, right? Because the current will now 0, and if the current is 0 here, so T1 and T2 turn off, and the T3 and T4 will be at also, it's not on, it is in blocking state. So during beta to pi plus alpha plus pi, you are getting the only this voltage E, right? Because all switching devices are not working, T1, T2, T3, T4. So you are getting the, okay, yeah, we have to draw this with the green so that you can understand that this is the, so I just remove first. So with the help of a different color, you can understand better, right? Now I'm just taking the green. So till beta, alpha to beta, you are getting the same voltage Vs, and after beta to pi plus alpha, you are getting the voltage E. Then again the same cycle will start, you are getting this kind of voltage. Just a wait. Like this only, right? Okay. So I'm just explaining like between alpha to, this is alpha, or alpha, this is alpha to beta, you are getting the same voltage Vm, but between beta to pi plus alpha, between beta to pi plus alpha, you are getting the voltage E, because all four devices are not working there, right? Because T1 and T2 get turn off and T1 and T3 will not turn on during that period between beta to pi plus alpha. So you are getting the only the voltage E, back EMF, right? So this is voltage E and this is Vm, right? So this is how, when your motor is working in a discontinuous mode, you are getting this kind of waveform. So now you can see that with the help of this converter, you can modulate the voltage or you can modulate the power also, right? Now we will try to find out the average voltage of discontinuous mode. So V0 is equal to the duration, because after pi, you are getting the same waveform. So the repetition will be after pi. So average value can be find out 1 upon pi, and so we are taking from alpha to pi plus alpha. Alpha to pi plus alpha, duration is pi, because after every pi cycles the waveform is same, like periodic waveform, and the duration of periodic waveform is pi, right? So alpha to pi plus alpha, Vm sine function, you can say d omega t, right? So in this you can say alpha to beta, you are getting the same Vm voltage. Alpha to beta, you are getting the Vm sine omega t d omega t, plus beta to pi plus alpha. Beta to pi plus alpha, you are getting the voltage E. This is constant voltage, right? Sin omega t, the integration sin omega t is the cos omega t. And this is alpha to beta plus E, and the integration is like pi plus alpha minus beta, right? This is Vm by pi minus cos omega t is, you can write like cos alpha minus cos beta plus E pi plus alpha minus beta. So this is how you are getting the input voltage, right? Now we can see also the speed of the motor with respect to your output voltage. So speed can be written as V0 minus IA RA upon K phi A, Ka phi A. So V0 can be replaced by this Vm by pi cos alpha minus cos beta plus E pi plus alpha minus beta, right? And this whole can be 1 upon Ka phi, and this Ia can in a similar way as I replaced this T is equal to Ka phi A. So Ia can be replaced by T upon Ka. So this can be written as T upon K Ra, because it's a DC separately excited, flux remain constant. So this is the relation between the speed and torque, and with help of both the characteristic, now we can able to try to so in the next coming class we are going to draw the characteristic and going to explain the characteristics so that you can understand how we will draw the, with the help of this waveform, how the motor will perform at a discontinuous mode and the continuous mode, how the characteristic will go. So because, and also you can see that in this the fully controlled rectifier is working in both the mode, like it is working in the motoring mode as well as the braking mode, first quadrant and fourth quadrant. We will see in the characteristics, right? So here I am now stopping. Next class we will see the half control rectifier and we will discuss speed torque characteristic of the fully controlled and the half control. Thank you.